Hi, welcome to lesson 22F, tree diagrams. Over the past couple of days, we've looked at theoretical probability, we've looked at tables of outcomes and compound events, and now we'll look at another way of setting up and to calculate probabilities using tree diagrams. So it's basically a way to illustrate sample spaces if we have maybe 2 or 3 different outcomes that we're looking at. If it gets a little bit bigger, like 5 or 6 or more, it gets a little bit crowded and a little bit difficult to draw the trees. So let's just dive right in and check this out. So a hat contains 3 red tickets and 2 green tickets. Why a hat would have 3 red tickets and 2 green tickets, I don't know. However, we've got 5 tickets altogether. So that's something that we have to kind of pay attention to. So we've got 5 tickets, 3 of them are red and 2 of them are green, and 2 draws are made without replacement. Okay, so that's the key there we have to pay attention to. We want to create a tree diagram that will show all the different probabilities. So there's the tree already set up for us. So here's us choosing, here's the first draw, and then there's going to be a second draw after that. And so in the first draw, well, there are 3 red tickets, so there's a 3 in 5 probability that we're going to select a red ticket. And there's a 2 in 5 probability that we're going to select a green ticket. Now, if we select a red ticket, well, there's 1 fewer red ticket left, and there's 1 fewer ticket in total left in the hat. So we subtract 1 from both of those, the numerator and denominator. So the probability of us selecting a red ticket after we've already selected a red ticket is now 2 out of 4. After we select a red ticket, there's a total of 4 remaining, but there's still 2 green tickets still in the hat. So that also has a probability of 2 over 4. Okay, so now suppose we happen to select a green ticket first. Well, there was a 2 in 5 probability of selecting a green ticket. So if we select a green again, so this is of course just random. We're just drawing our hand, putting our hand in the hat and pulling out a ticket. There's a 1 in 4 probability of selecting a green ticket on the second draw. And there's still, so after the green ticket has been pulled out, there's still 3 red tickets left. So there's a 3 in 4 probability that we're going to select a red ticket. Notice here that the probabilities, so because we're going to pull out a ticket, there's a 3 in 5 probability that it's red, or 2 in 5 probability that it's going to be green. So if you add those 2 probabilities together, it equals 1, which means that it is with all certainty, we are definitely going to pull 1 ticket out of the hat. Then in the second draw, we have a 2 in 4 probability of pulling out a red ticket and a 2 in 4 probability pulling out a green ticket. Again, we've got 1 of the 2 and 1 of the 2 in simplified form, meaning that we will definitely be pulling a second ticket out of the hat. And 3 out of 4 and 1 out of 4, of course, that equals 1 again, meaning, again, we are definitely going to be pulling out a second ticket. Okay, so just to notice that those probabilities will add together to be 1. So in order for us to find the probability that there will be a red ticket drawn after the first red ticket is drawn, we then take these probabilities and we're going to multiply 3/5 by 2/4 or 2/4, and so we're going to have 6/20. If we pull a red and then a green, well, the red is still, the probability is 3 over 5, and the green then is 2 over 4, and it is also 6 out of 20 probability of selecting red and then green. If we select green and then red, we're going to have a 2 in 5 probability of selecting the green, followed by a 3 over 4 probability of selecting a red after that, which is 6 over 20. And then we're going to, if we have a green followed by the second green, we're going to have 2/20 probability of pulling out 2 green tickets. So as we add up all these probabilities, and generally I wouldn't simplify these necessarily. Sometimes it's better just to leave it in unsimplified form, because there are some instances where maybe you might have like a 1 in 20 in one of these, or a 3 in 20, and then they wouldn't simplify. So you'd have to get a common denominator anyways. So why not just leave it in the unsimplified form, and then we can just add it all up and we get 20/20, which obviously is 1. So we are definitely going to get one of these possible combinations. So that's why the probability, the sum of all those probabilities, is 1, because we were definitely going to get either 2 red, a red and green, a green and a red, or a green and a green. Okay, and that's basically how we're going to be using the tree diagrams. We're just going to be multiplying the probabilities that are along each branch as we go. Okay, and maybe if I were to just highlight this, we got red followed by red will give us this, and then, well, actually I don't want to start going through everything, but I'll do green followed by red will give us this one. Okay, so you get the idea. And we're always multiplying them because for every probability of us pulling out a red ticket, there's going to be a probability of us pulling out another red, or like this 2/4 probability of pulling out a red ticket. So for each one of those 3 probabilities, 3 red tickets, they each have a 3 in 5 probability of being pulled. So for each one of those 3, we've got a 2 in 4 probability of picking out one of these 2 red tickets. Okay, so that's why we get the 6, because there's 3 tickets followed by 2 tickets, so we get 6. Okay, so that's kind of how that works, and that's why we're multiplying them together. Okay, so just going along here, the probability for each color, for either color ticket, is marked times branches, which I've shown you. There are 4 alternative branches, each showing a particular outcome. All outcomes are represented. So the 4 alternative branches are the second branches. The probability of each outcome is obtained by multiplying the probabilities along its branch. So to find the probability of selecting 1 red and 1 green, well, we've got those situations up here. So 1 red and 1 green is this and this. So we've got 6/20 for each of those. Okay, in this particular question, we're not asking about specific orders, just selecting a red and selecting a green. So we've got 6/20 probability of selecting in one order, and then 6/20 in the other order. Therefore, we have a 12 in 20 probability of selecting red and green, and it doesn't matter the order. And then now in this case, I can just simplify that. So we divide top and bottom by 4, so I get 3/5. Okay, so it's a 3 in 5 probability that we will select a red and green ticket. So now for the second example, we're looking at the probability of selecting at least 1 green ticket. So at least 1 green ticket means 1 ticket, 1 is green or 2 is green. Okay, so we can say here, sorry, I guess we just have to write it, at least 1 green. Okay, so the outcomes is either red green, green red, or green green. So we can do one of a couple of things. We can either add those three probabilities together, which we'll do. So 6/20ths plus 6/20ths plus 2 out of 20. So I guess I shouldn't say 20ths, but 6 out of 20 probability of selecting red then green. Then there's a 6 out of 20 probability of selecting green then red. Or there's a 2 out of 20 probability of selecting green then green. So that gives us a probability of 14 out of 20, which is 7 out of 10. Okay, which is 70% probability of us selecting at least one green ticket. So, but what we could do though is we can say, well, at least one green is equal to 1 minus no green, right? So 1 means that we're going to select 2 tickets. And no green is the first probability of it being 2 red. So if we do the probability of at least 1 green, it's 1 minus the probability of no green, which is the probability of 2 red. And probability of 2 red, if you remember, is 6 over 20. Okay, so that's up here. 2 reds is the probability of selecting 2 reds is 6 over 20. So it's 1 minus 6 over 20. And of course, 1 can be written as 20 over 20 minus 6 over 20, which gives us 14 over 20, which gives us, again, 7 over 10. Okay, so whether we do the complement by subtracting from 1 or by adding up all the individual probabilities, we still get 7 out of 10 probability that we're going to select at least one green ticket. Carl is not having much luck with his car or his transportation these days. His car will only start 80% of the time, and his motorbike will only start 60% of the time. Well, this guy's pretty lucky in my books if he has a car and a motorbike, but anyways, if they don't work all the time, then what's the point? So we want to draw a tree diagram to illustrate this situation. So basically, we've got one vehicle, either it starts or it doesn't, and then we got another vehicle that either starts or it doesn't. So we can organize this by saying, well, vehicle 1, maybe that's the car, and vehicle 2 then. So if he wants to go to work by car, he would try that first, and if he can't get his car working, then he'll try his motorbike. So so let's say there's car will start and car will not start. And so we draw it. Now I should be drawing these with rulers, so I apologize. So 80% of the time the car will start. So we've got 0.8. So we'll write the 80% in terms of a decimal. And the car not starting then, of course, will be 0.2 or 20% of the time. So then whether the car starts or not, the bike also has either starting or not starting, those probabilities. So the bike's only going to start 60% of the time, whether the car started or not. So it doesn't really matter. The bike starting doesn't depend on the car starting. And if the car doesn't start, again, the bike could start. It starts 60% of the time, or the bike may not start, and that's 40% of the time. Or even like probability of the of it starting or not starting. So then we've got car starting and bike starting, which is 0.8 multiplied by 0.6. We've got the car starting and the bike not starting, which is 0.8 and 0.4. And then we've got the car starting and the car not starting and the bike starting. So that's 0.2 multiplied by 0.6. And then we've got neither the car starting nor the bike starting, which is 0.2 by 0.4. And then we multiply those together. So of course, so if they both start, it's still only, that's less, if they both start, it's less than 50% of the time, or the probability is less than 50% of them both starting. And then if the car starts and the bike doesn't, that's a 32% probability that that'll occur. The car not starting and the bike starting is 12% probability. And then the car not starting and the bike not starting is an 8% probability that that will occur. And if you add all these together, we get 1, because one of these events will occur. Okay, it's with 100% certainty that the car will either start or not, and the bike will either start or not. And those are all the outcomes that are possible here. So now we've got all the probabilities written out here. We've got the tree diagram. So now we can use the tree diagram to determine the chance. I'm going to write this as probability. I think that's a better word for this. Probability that both will start. Well, we've already calculated that. And that's 0.48 from above. And then that the probability that Carl can only use his car. Okay, well, there's a couple possibilities here. He can only use his car. Well, actually, sorry, there's only one possibility. And Carl can only use his car in this situation where the car starts and the bike doesn't. And that's already been calculated at 32%. So only the car will start, which is 0.32. Okay, so that's that probability there. Now we have two boxes, box A and box B, and they each have 6 petunia plants in them, which aren't flowering yet. We know there are seeds in there, or bulbs, or whatever petunias, however petunias grow, but we don't know the color of the flowers yet because they haven't blossomed yet. We do know in box A, 2 of them are purple and 4 of them are white. And in box B, 5 of them are purple and 1 of them is white. So what we're going to do first is we're going to flip a coin first. We're going to flip a coin to see which box we're going to use. Okay, so we have to select the box first. That's the first thing we have to do, because we're trying to find the probability that the flower, the one flower that we remove, or the one plant we remove, will have purple flowers. So we have to select the box first. So it's either box A or box B. Again, should be using a ruler, so I apologize. And if we're flipping a coin, we've got a 50% chance that it'll be heads, and therefore box A will be chosen, or 50% of the probability will be that box B is chosen if a tail turns up. And then we look at the flower. So we're pulling out a plant, and so it could be purple or it could be white. whether it's from box A or box B, purple or white. And from box A, purple is 2 out of 6. Actually, I should have even, maybe I'm just going to go back here and keep it all in fractions. So I kind of like that better. So this is 1/2, and this is 1/2 as well. White, we've got, well, there's 4 white plants in there, so 4 out of 6. The purple in this box is 5 out of 6, or 5 over 6 probability, and white, there's just 1 over 6. Okay, and then so the number of outcomes is, for our outcomes, we've either got box A, purple flowers, or box A, white flowers, or we could have box B and white flowers, or box B and, sorry, I'm going to change this to purple here, box B and purple. And so then we just have to multiply the probabilities along the arms. So the probability then of us choosing a purple or a plant that has purple flowers is, if it's box A, we multiply 1/2 by 2/6, or 2 over 6. So we're going to have 2 over 12. Box A and a white flower, the plant with a white flower will be 1 over, 1 over 2 multiplied by 4 over 6. And that gives us 4 over 12. Box B again is 1/2. So if we chose box B, there's 1 over 2 probability. The plant with the purple flowers would be 5 over 6. So we get a 5 over 12 probability that will occur. Or if we choose box B, or select a flower from box B, and it happens to be white, we've got a 1 in 12 probability that will occur. And if we add all these together, 2 plus 4 is 6, plus 5 plus 1 is 6, we get 12 over 12, which is 1, which means that we will definitely be choosing a plant from one of those boxes. And we want to then determine what probability is that the plant that we choose has a purple flower. Well, here's from box A, we get a purple flower, and there's a 2 in 12 probability of that. Or from box B, the plant has a purple flower, and there's a 5 in 12 probability that occurs. So the probability of the plant having a purple flower, we add the probabilities together. 2 over 12 probability that comes from box A, plus 5 over 12 probability that comes from box B. Therefore, we have a 7 in 12 probability that we will select a plant with a purple flower. Okay, so that is it for this lesson. Hopefully that has sort of cleared up any mystery about tree diagrams, and now you can see the forest for the trees. So have yourselves a great afternoon. Thanks for watching, and we'll see you in class.